Rust smart pointers. Smart pointers are types that act like pointers but have extra capabilities. Regular references borrow data without owning it. Smart pointers own the data they point to. They add features like heap allocation, reference counting, and interior mutability. In this video, we cover box, RC, arc, and RefCell. Box is the simplest smart pointer. It puts data on the heap instead of the stack. The value is stored on the heap, and box is a pointer on the stack. When box goes out of scope, the heap memory is freed automatically. Use box for large data, recursive types, and trait objects. Recursive types are the most common use case for box. A linked list enum that contains itself has infinite size. The compiler cannot calculate it. Box fixes this because a pointer has a fixed size. Now the cons variant stores a value and a pointer to the next node, not the entire list. Box is also needed for trait objects. When a function returns different types that implement the same trait, use box-dyn trait. The compiler does not know the concrete type at compile time, so it needs a heap-allocated pointer. This enables runtime polymorphism in Rust. The deref trait lets you use the star operator on your type, just like a reference. It also enables deref coercion, which automatically converts between reference types. When types do not match, the compiler calls deref as many times as needed. This is why you can pass a box string where a str reference is expected. The drop trait runs cleanup code when a value goes out of scope. Values are dropped in reverse order of creation. If resource 2 depends on resource 1, resource 2 is cleaned up first. You can drop a value early with the standard drop function. You cannot call the drop method directly to prevent double-free bugs. RC enables multiple owners for the same data. RC clone does not copy the data. It only increments the reference count. The data is freed when the last RC is dropped and the count reaches 0. RC is perfect for tree structures where nodes can have multiple parents sharing the same child. Important: RC is not thread-safe. It only works in single-threaded code. The reference count is not atomic. If you need shared ownership across threads, use arc instead. We will cover arc in a moment. For single-threaded programs, RC is the right choice. RefCell provides interior mutability. Normally, you cannot mutate data behind a shared reference. RefCell moves the borrowing rules from compile time to runtime. Use borrow for shared access and borrow mut for exclusive access. If you violate the rules, the program panics at runtime instead of failing at compile time. The most common pattern is RC RefCell T. This gives you shared mutable data in single-threaded code. Multiple handles can read and write the same vector. RefCell checks the borrowing rules at runtime. This pattern is useful for graphs, caches, and any data that needs multiple owners with mutation. ARC stands for Atomic Reference Counting. It is RC for multi-threaded code. It uses atomic operations to safely update the count for multiple threads. ARC is slightly slower than RC because of the atomic overhead. Use RC for single-threaded code and ARC when you need to share data across threads. For mutable shared data across threads, combine ARC with mutex. ARC handles shared ownership. Mutex handles exclusive access with locking. 10 threads can each clone the ARC, lock the mutex, increment the counter, and the final value is correct. This is the standard pattern for thread-safe shared state in Rust. Here is when to use each smart pointer. Box for heap allocation and single ownership. RC for multiple owners in single-threaded code. ARC for multiple owners across threads. RefCell for interior mutability. RC RefCell for shared mutable data on one thread. ARC mutex for shared mutable data across threads. A common mistake is using RC in multi-threaded code. The compiler catches this with a clear error message saying RC is not send. The fix is to use ARC instead. Another mistake is creating two mutable borrows on a RefCell at the same time. This causes a runtime panic. Drop the first borrow before creating the second. Watch out for reference cycles with RC. If two RC values point to each other, the count never reaches 0 and the memory leaks. Use weak references for backpointers. This is important for tree structures where children point back to parents. Weak does not increment the reference count. Start simple with own values and references. Need heap allocation? Use box. Need multiple owners on one thread? Use RC. Need multiple owners across threads? Use arc. Need to mutate shared data? Add RefCell for single thread or mutex for multi-thread. Most Rust programs only use box and occasionally arc mutex. Here is a summary table. Box heap allocates a value with single ownership. Deref makes a type behave like a reference. Drop runs cleanup when a value leaves scope. RC is reference counted shared ownership for one thread. Arc is atomic reference counted for multiple threads. RefCell provides runtime borrow checking. In the next video, we will learn concurrency, threads, channels, and mutexes. We will see how arc mutex works in practice and why Rust's ownership system makes concurrent programming safe. Rust calls this fearless concurrency because the compiler catches most bugs before your code runs. If you like this video, hit the like button and subscribe for more tutorials.